Yeah, so this talk will be about indeed a project I did a couple of years ago with Jesse Hahn when I was a postdoc at the University of Pittsburgh. And so we formalized in Lean that the continuum hypothesis is independent from the normal axioms from set theory, the ZFC Zermelo-Frankel axioms with choice. And because I assume that most of you are not logicians, set theorists, model theorists, I will most of this talk explain like what does that mean, how do you prove these kinds of things, and then only a little bit talk about actually what goes in the details of the proof. Let's start with defining what is the continuum hypothesis. So some of you probably already know this, but so one way of saying what the continuum hypothesis is saying that there's no set whose cardinality is strictly between that of the natural numbers and that of the real numbers. So I think most of you know, like there's a counter diagonalization argument that says that the cardinality of the power sets, the cardinality of the power sets of the natural numbers is larger than the cardinality of natural numbers. There's more subsets of natural numbers than natural numbers. And that the real numbers have the same cardinality as the power set of the natural numbers. But now the continuum hypothesis is a statement that there's no cardinality between those two. So if you have a subset of the real numbers, it's either countable or is in bijection with the real numbers. And so in 1963, Paul Cohen, together with other people, proved that this is actually neither provable nor disprovable from the axioms of set theory. So that is kind of surprising that, I mean, this is like not too complicated statement, and set theory doesn't say anything about it. And so the project I did with Jesse Hahn, we called the FlyPitch project, which is almost an acronym for formally proving the independence of the continuum hypothesis. We formally proved this in Lean 3, the previous version of Lean. We lost me on the screen. Oh, what is happening? I'm asked. Is it better now?
Yes.
Okay.
Thank you.
Okay. Okay. So some history. Oh, I don't have focus on my slides now. Yes. So some history of the continuum hypothesis. So originally this was formulated and conjectured by Georg Cantor in the 19th century. And he actually thought that this would be provable from in set theory. So that's what he conjectured. And the continuum hypothesis was actually the first problem of Hilbert's 23 problems. So then a couple decennia later, Kurt Gödel actually proved that ZFC cannot disprove CH. So he showed that the continuum hypothesis is consistent with ZFC, and he did this by constructing the universe of constructible sets. So they form a model of set theory, and thereby he shows that like set theory is consistent with the continuum hypothesis. And then in the 60s, Paul Cohen proved the other part of it by showing that CFC can also not be proven in set theory by introducing a notion of forcing, which is a powerful notion in set theory to construct sort of other models from like existing models. and that sort of unleashed sort of modern set theory. Like forcing became like a very important part of set theory after that. And actually, Cohen got a Fields Medal for his work on forcing, and that is, I believe, the only Fields Medal that was ever awarded for something in logic. So that's also shows sort of that this is was an important result. So in our formalization, we didn't use the same proof that Kurt Gödel and Paul Cohen gave. So there's two main ways that we diverged from the proofs that were originally given. So instead of forcing uses something called a forcing poset, and actually we used a different technique using Boolean-valued models that I'll explain later. And this was introduced by Zalafay and Scott also in the 60s. And one thing that was interesting is we proved both directions using forcing. So we first proved sort of the hard direction that by constructing a model where the continuum hypothesis is false. And then we had this technique of forcing, and we thought, well, we have this hammer, and we need to prove this other thing that looked very much like a nail. So we slammed the hammer on the nail, and also proved that the continuum hypothesis is consistent with set theory using forcing, which is not a new proof, but it's not the standard proof. Okay, so these statements are maybe kind of weird from a mathematical perspective. Like in mathematics, we like proof statements. We sometimes disprove statements by giving counterexamples. But how do we actually prove that something cannot be proven? And we're talking now about proofs. And so in this talk, I'll give you a bit of a crash course in first order logic to talk about like what is a proof. In order to make sense of like formally saying that you cannot prove this. And one thing I should mention is first order logic is not the logic of Lean. It's a simpler logic that makes it easier to reason about. But unfortunately, this will not tell you too much about like the internals of Lean. Okay, so let's get started. So first order logic is not like the logic of a single theory, but you can formulate many theories in it, and it gives you sort of a framework for these kinds of theories. And so a theory in logic starts with a language. You need a language to know like what kind of functions and relations you can talk about. And so because we've all been learning Lean in the last week, I'm going to show you some of the definitions in Lean code. And so, for example, this is one that I expect that most of you can read what this means, but let me also explain it. So I'm saying a language is something that contains functions and relations. And so for every natural number n, we have functions, we have a type of functions, or function symbols, I should maybe say, in that natural number. And that natural number is interpreted as the arity of the function. So we sort of have a collection of functions, and each function has an associated arity to it. And the same with relations. We have some relations with a given arity. And so here are some examples of languages. For example, we can define the language of groups by having three function symbols. So we have, in the language of groups, we have a multiplication. And I didn't write it on the slides, but so the multiplication is, of course, a binary function. It takes 2 arguments. Then we have a constant 1, say, and that is a constant, but we can treat that as a nullary function that doesn't take any arguments. And we have an inversion, which takes 1 argument and gives you the inverse in a group. And so I gave some other examples. So for example, in ordered rings, we have an addition and multiplication, which are binary, 2 constants, a unary negation. And then we have a binary relation symbol. We have a less than or equals, which given 2 terms, I can compare them or not. And I mean, and we can formulate many things in using languages. So for example, we can define the language of modules over a fixed ring. by saying like in the module we have addition, zero, and unary negation, and then for every constant in the ring we have a unary function that is like scalar multiplication by that ring. I should say here that what I wrote in the footnotes, that we're doing what I'm describing here is single sorted logic. So we have only one type basically. There are other variants of logic where you have like multiple types, and then you can also say like, oh, we have one type for the elements in the ring and one type for the elements in the module. But yeah, so even if you only have one type, you can sort of still, for a fixed ring, talk about the modules over that ring. Yes.
When you say L group, you mean that L group is a term of type language?
Yes. But of course I'm a bit sloppy here. I should like really say that like there's one function 0 contains this element, function 1 contains this element, and function 2 contains that element.
So functions. So is that literally in code, or am I?
No, so this is literally in code, and this is not.
Okay,
But
would it be true if you were formalizing an L group?
I could define an L group which has one multiplication which is binary, one inversion which is unary, and one constant that is nullary. Yeah. And so for example, the language of sets, it doesn't. I mean, usually how it's formulated is without any function symbols, and you only have one relation symbol, membership. And that is the simplest way of formulating set theory. And there's many other things you can write in languages. So then once we have a language, we can talk about what are terms in this language. And before I talk about what terms are, I want to give you, so one thing that Lean has is called inductive types. I don't think we've talked about that in this week, so let me give you a little bit of an introduction to inductive type. So an inductive type is sort of it is a way to generate like initial types of a certain algebra, or if you don't know what that means, it means like it's the smallest type that contains certain constructors. So here I give you almost Lean codes of how their natural numbers are defined, except that I use like this Unicode symbol nat, and in the actual definition, nat is written out. But what I'm saying here is the natural numbers are the sort of the smallest type that contains a 0 and that contains a successor function. And sort of the natural numbers are generated by those two constructors. And then I'm implicitly sort of saying, oh, and the successor is never 0 and is injective.
I think 0 bars with that.
And exactly, yeah. It's pseudo Lean code. You're right. So the inductive types give you a way of sort of saying, oh, so a natural number is either 0 or a successor. And this also gives a way to define terms. So I'm now defining, given some language L, I'm defining what are the terms that have 3 variables maybe in some type alpha. And so what it means is a term is either a variable, so either I take one of these variables in type alpha and I construct the term that is just that variable, or it is a function applied to already existing terms. So I take a natural number n and I take an n-ary function symbol f that is in my language, and then I take this is sort of a vector of terms that I've already constructed, and then I get a new term. And sort of the terms are sort of the least type that is generated by these variables and these functions. And so here are some examples. So in the language of groups, a single variable x is a term in the language of groups that has a variable x. And I can also use function symbols to generate these terms. So this y times z, it's really like the function symbol of like multiplication applied to like the vector, or sort of I guess the lean notation is with this exclamation mark, y as the first argument, and the second argument is y times z. So that is again a function symbol of multiplication of vector y and z. So this would be how this term, how times z is encoded as a term in this language. And it also makes clear that it's much nicer to write this than to write what I wrote on the blackboards. But I sort of see that these terms are sort of all the, I mean, they are the expressions you can write in a group. So, I mean, these are words in a group. And like, here's another one you can, I mean, this you wouldn't write on paper because, I mean, how often do you write one inverse? It's just one. And how often do you multiply explicitly by one? But this you can all write down. And so in the language of sets, we didn't have any function symbols. And so all the terms are variables. So then we have terms, and then we would like to say things about these terms. Maybe we want to say two terms are equal sometimes or always. And that's where formulas come in. So terms are the objects in your sort of that you reason about, and the formulas are the statements that you say about these objects. So formulas are sort of, I mean, you should really think of like prop in Lean, so the proposition. So what are the formulas? Well, we have the bottom element, which is the false formula. We given two terms, t and s, we have the formula t is equal to s. So equality is sort of a special relation that we always have in the logic. And then for any relation symbol that I had in my language, any n-ary relation symbol r, if I have n terms of this relation symbol, if I have n terms in my language, then I can apply the relation symbol to it and get a valid formula. And then, I mean, I can define like all the binary connectives of two formulas are formulas. So if phi and psi are formulas, then like all these things are formulas. Of course, you don't need all of them. Especially if you work classically, you can, like, I think you can only deal with just false and then implication, and then all the other binary connectives can be defined. And then we have quantification. And quantification is the reason that I don't show Lean code here, because quantification is a little bit finicky, because we have to deal with like variables and variable capture. So when I write for all x and then a formula, so quantification just says if phi is a formula, I can write for all x in front of it, and that's a new formula, or exists x. But the meaning of that is a little bit finicky, because I have to say like, oh, all the x's in phi are sort of captured by this quantification. And doing that, and this is exactly the same as like if you do an integral, like the integral of f of x dx, this x is captured by this integration. And doing this completely formally is actually a little bit finicky. Cesare talked in the previous talk about like packages that some languages can deal with this very well. In Lean, we used sort of we did it without like special support. But we did it with a technique called de Bruijn variables. And people that are on Zilip for a while might now be scared because they've seen someone, maybe me, explain the de Bruijn variables, and they're kind of confusing. But they're a way to deal with this variable capture in, once you know what you're doing, a nice way. And so the variables that are not captured by any quantification, they're called free variables in the formula. Yes.
Is that the definition of a relation symbol?
No, so a relation symbol is something that I had in my language. So every language came with some function symbols and some relation symbols. And then this says once I have a relation symbol in my language, then I can apply it to the right number of terms to get a formula. So let me quickly flash what this is in Lean. So we sort of have this n, which is sort of the number of bound variables, is how you should think of it. And we have these bounded formulas, and then the formulas are the bounded formulas that have no unbound bound variables, sort of. But I don't want to dig too deeply into this, so let me just move on. So then the important formulas are the formulas that don't have free variables, and those are called sentences. So those are actually true-false statements that that say, I mean, the statements that have a true value. And then a theory is just a set of sentences. So here are some examples. So for example, the theory of, so I just talked only about the language of groups, but groups also have axioms. So now I can give you the theory of groups, so the axioms of what it means to be a group. And these are three axioms you can write down to axiomatize a group. So the first one says every group element, for every group element G times 1 is equal to G. And so, of course, this G is bound by this quantification. It doesn't have any free variables, so this is a sentence. So that's a thing I can write in my theory. And then these other, and so this second one is associativity of multiplication. And of course, this is sort of a syntax I use for repeated quantification. And then the last axiom says every group element has a right inverse given by G inverse. So this is the theory of groups. And then the axioms of set theory are also written sort of in this way. I'm not going to show you all the axioms of set theory because some of them are, I mean, a bit complicated to parse. But here are 3 of them, at least in usual representations. So the first one says there exists an empty set. And let's see what it says. So there exists an S, which we think of as the empty set, such that for all x, x is not an element of S. I mean, that sounds like it characterizes the empty set to me. And the second one says we can form this set, basically. So it says for any 2 sets x and y, there exists a set S, and then we characterize the elements of S. Namely, z is an element of S if and only if z is equal to x or z is equal to y. So that gives the pairing axiom. And then the next one gives the power set axiom that says, like, given a set S, I can give this set P, which is the power set, which is supposed to be the power set of S, and elements of P are precisely the subsets of S. And here you already see, oh, well, with only this memberhood. So this is really the formula in the language, but really what we want to write here is T is a subset of S. And so we kind of want to define these relation symbols, which I'll come back to in 2 slides. And so, okay, so we have terms, the objects that we want to reason about, the formulas, the statements that we can do, and now we can precisely define what a proof is. And a proof is just often it's written as a tree, so some proof tree that, like, at each step has a formula, and at the bottom it has a conclusion. And if I restrict myself to only false and implication and universal quantification, which are enough to define all the other quantifiers and connectives, then this is a full rule set to define provability. And I don't expect you to read all of this, but I mean, so let me go through maybe one of the a few of them. So the first one just says, well, so how you should read this symbol is from so gamma is a set of sentences, set of formulas. So from this set of formulas gamma, I can prove the formula phi. And And these are formulas, so they could have free variables. So the first rule for provability says if phi is an element of gamma, if it's an assumption, then I can prove phi. You might recognize the assumption tactic here in Lean. And so, for example, if I jump to the third one, it says if gamma can prove phi and gamma can prove phi implies psi, then gamma can also prove psi. And you can sort of, and this gives sort of a tree nature of this of a proof because like at the bottom we have gamma proofs psi, and it's often written with this horizontal line that like gamma proves phi and gamma proves phi implies psi, and then like above here you get like a proof of this part, and above here you get a proof of this part, and that sort of looks like an upside down tree, or not an upside down tree, right side up tree. I don't know how trees work in the real world. Yeah, and then so we have some. So this is the axiom, the rule that makes the logic classical. So this is proof by contradiction to prove that gamma proves phi. It is sufficient to prove a contradiction from the assumption that phi is false. So this is just a negation of phi, of course. And then we have some rules for quantification, which are a little bit complicated, and then we have two rules for equality. So we have a precise definition of what it means in first-order logic to prove something, to prove a statement from a set of assumptions. Yeah, and so now I want to go back to these defined relation symbols we had in the set theory. So in set theory, we only have this one predicate, one relation symbol membership. But if we run to, and we can in theory write every statement in set theory as a formula using only that predicate, but that becomes very unwieldy. So we want to define these other predicates. So we want to define, for example, S is a subset of T, some predicates like alpha is an ordinal, F is a function. So F is a function. So in set theory, everything is set. So functions are also set, but you can encode sort of functions as sets by like encoding its graph, for example. And you can encode things like there exists a surjection from S onto S, from S onto T. And so these relation symbol, like first-order logic doesn't actually talk about definitions very much, but you can sort of add them to the language. And then there's a theorem about in first-order logic that if you only add definable things to your language, like you cannot actually prove anything more. So we can add these relation symbols. We can also add like operations on sets. So for example, I want to add some cardinal. So for example, the Aleph not, which is the least infinite cardinal. And for example, the power set operation. And those are all definable in, like uniquely definable in set theory. And then there's theorem that says that adding them as actual function symbols and actual relation symbols doesn't actually improve what you, increase what you can prove. So we can add them to the language. And then using these extra function symbols and relation symbols, we can, for example, state the continuum hypothesis as for each set S, either there's a surjection from S onto this set, which is the least infinite, a set with the least infinite cardinals, or the countable infinite set, or there's a surjection from, or no, sorry, the other way around. There's a surjection from the least infinite set onto S, or there's a surjection from S onto the power set of the least infinite set. And so that's how you can write the continuum hypothesis in set theory. And then the independence of the continuum hypothesis says that these axioms that I've partially given to you of Zermelo-Fraenkel set theory do not prove the continuum hypothesis, but they also don't prove the negation of the continuum hypothesis. So that is the statement of the thing that we formalized. Yeah, and then this I already mentioned. So actually adding these function symbols and these relation symbols, that's what we did in the formalization, but then they don't actually increase what you can prove in your language. So how do we prove that there's no such, that these proof trees don't exist? Yes, question.
Did you define an inductive type whose terms are sort of pairs, gamma, psi?
So this provability, this is really indeed an inductive type in Lean. So there's an inductive type that says like, oh yeah, this is what the provability relation gives. Yeah. Yeah. For when you plug it in the theory of set theory and the formula, the continuum hypothesis. Yeah, exactly. That is the formal statement in Lean. So we've talked about provability, but we can also talk about the semantics of formulas. And so we can interpret like terms and formulas inside a model. So to talk about models, we first need to talk about structures of a language. So if you have a language L, then a structure of that language consists of three things. So it consists of just a set, the carrier set. And then for each function symbol, f, we must have an interpretation of that function symbol in your model. And that should be, of course, an n-ary function. So it should be a function from m to the n to m. And for each relation symbol, we should just say where is this relation, does it hold? So it's an interpretation of the relation symbol R, and it's just a subset of m to the power n. And so, yeah, so a structure of, for example, the language of groups is just any set that has a binary operation, which we call multiplication, and distinguished element 1, and an unary inversion operation.
Yeah, when you say set,
Yeah, for example, type in Lean. Yes, yeah. Yeah, exactly. So sort of. I'm not talking about like an object in the language of set theory or something. Yeah. And then inside a model, so we have interpretations of functions and relation symbols, and then we can of course also interpret terms and formulas. So if we have a term in the language L, which might have some free variables, then we can also interpret that term as an element in M, assuming that we have interpretations of all the variables in the that occur in that term. So if, for example, if t is this term, which as a reminder was just the term y times z, as long as I have interpretations of y and z in my structure, then of course then this is also an element of my structure just by applying this multiplication function to it.
So by interpretation, you mean an element.
Yes.
Term y and
exactly. For each variable in my term, I should have an element of m. Exactly. And then if phi is a formula, a statement about these things, then I have then this is either true or false in M, assuming again that we have interpreted all the free variables in that formula. So if, for example, y times z is equal to z times y, if I have an interpretation of z and y, then this is either true or false. And if I have a sentence, so that is something without free variables, so that might be something like, for y there exists a z such that this holds, then, I mean, this is something that is just either true or false in my structure M. and depending on depending on M, this is either true or false. But so every sentence has a true value in a structure. And then a model of a theory. So a theory was just a set of sentences. Then a model of that theory is just a structure where all the sentences in that theory are true. And so, for example, a model in the theory of groups is just a group. It's just a set with some operations that satisfy the axioms of the groups. And a theory, and so a model of the theory of rings that I haven't given you is just a ring. And of course, we are going to try to construct models of the theory of Zermelo-Fraenkel set theory. And then there's one more notion that is important. So if gamma, again, is a set of sentences, and we write this gamma models phi, that means that for every model of this theory gamma, the sentence phi holds. So that says that if every model where all the sentences in gamma hold, phi also holds. And so this sort of gives a semantic interpretation of this. And now we have these two notions. We have provability, gamma proves phi, and the semantic notion, gamma models phi. And how do these notions relate? And this these are two important theorems. There's the easy direction, the soundness theorem, that says if I can prove phi from gamma, then actually in any model where gamma is true, phi is also true. And then the harder thing, this is called Gödel's completeness theorem, not to be confused with Gödel's incompleteness theorem. That says that if in every model where gamma is true, phi is true, then actually I can prove phi from gamma. And so to show that some theory doesn't prove phi, it's sufficient to construct a model where phi fails. And actually, for this step, we only use the easy soundness theorem. We don't actually need the completeness theorem. But we actually also formalized the completeness theorem just as a first step towards like working with first order logic. But then we didn't actually ended up using it for the rest. So we want to construct models of set theory. But as I mentioned a bit earlier, we don't want to just construct models. We actually want to construct Boolean-valued models. So those are a bit more complicated. And the idea is that, as I said, every sentence or in a model is either true or false. And we want to sort of weaken that by taking a Boolean algebra. So Boolean algebra, do people know what that is? So it's a partially ordered set which has like actually we usually work with complete Boolean algebra. So that's a partially ordered set where every set has a supremum, a least upper bound, and infimum, greatest lower bound, and where we have negations. So for every element there's a negation that so. For every element x, we have an element negative x in the post set such that their least upper bound is the top element of the partially ordered set, and their infimum is the bottom element. So and these complete Boolean algebras sort of you can do logic in them because, for example, we have these infimum. So there's an infimum operation. So like x infimum y, and this corresponds sort of to the conjunction of the propositions x and y. But we think of these as true values. So instead of having true and false as true values, we now have true values in like many more in a Boolean algebra. And then structure